Okay, so we're going to take a look at this problem number 82 so that we can do an energy level diagram, and then we'll probably do the one above because it also has an energy level diagram. Actually, we'll do 87 next because it's not a triangle problem. Okay, so chloromethane, CH3Cl, a compound found throughout the environment, is formed in the reaction of chlorine atoms with methane. Calculate the enthalpy change for the reaction of CH4 gas and chlorine atoms, presumably gas, to give a CH3Cl gas and HCl gas. Is the reaction exo or endothermic? And then draw an energy level diagram that shows how the various enthalpies in this problem are related. Okay, so here's the reaction. CH4 gas plus 2 Cl gas gives you CH3Cl gas plus HCl gas. And we're supposed to calculate the enthalpy change of the reaction. So for this reaction, what we're going to do is we're going to be using this.
Tony, I don't think you're showing the problem you've written down.
You know what? Maybe I zoomed in too much and I kept it zoomed in. Thanks for saying something. I would have just gone the whole time without doing anything about it. I'm not quite used to putting this F next to the delta. Usually in previous textbooks, we put the F next to the H on the other side. So that's why I keep doing this. So this is what we're going to do for this particular problem, which means that for CH4 gas, Cl gas, CH3Cl gas, and for HCl gas, we need the enthalpy of formation for each of these. So I'm going to look these up in the back of the book real quick. I'm not going to show you where they are in the index. I'm just going to look them up. If you want, you can look them up also and make sure I'm not writing down something that's incorrect. So for CH4, we have negative 74.87, and that's kilojoules. For CH3Cl, I'm not finding it. Let me read the problem again. Well, it must be here somewhere. I'm just not seeing it. Okay, well, there's HCl. Cl is and I'm going to look one more time for the CH3Cl. And I don't find it. So maybe it's in the book somewhere in the chapter, which is a shame. All right, so since I can't find it in the back of the book, I'm just going to look it up for on the internet. So I'm going to write enthalpy of formation. Because you don't want to write all that triangle stuff on the internet. It's just too much trouble. Enthalpy of formation. And usually if you write the formula out the way it's written without regard to uppercase or lowercase, it works out pretty good. Okay, the enthalpy of formation for methyl chloride is minus 82.68. So this one I had to find on the internet. Okay, so when I plug the numbers in here, I like to put brackets for the products and brackets for the reactants. So I have one CH3Cl. So I'm going to have 1 times negative 82.68 kilojoules plus, because of that, 1 HCl, 1 times negative 92.31 kilojoules, and then minus 1 times CH4, negative 74.87 kilojoules, and then plus 2 times 121.3 kilojoules. Okay, so what I'm going to do is I'm going to add these two together first, and I should get around minus 174, right? Or minus 175, pretty close to that. So 82.68 plus 92.31 is equal to 174.99 kilojoules. And because that's a negative and that's a negative, of course, this is a negative. And then here I have a negative and then 2 times a positive. This comes out to be about 240. Minus 74 makes it around 180. And it's going to be a positive 180, but that negative will make it a negative 180. But we'll do this one step at a time. So 121.3 times 2, and then minus 74.87. And we get 167.73. This is only good to the 7 because of this 3 kilojoules. And so we have minus 174 minus a positive 167. So we essentially just add them together, and we're going to get a negative 330-ish or something like that. So 342.7 kilojoules. And that is the enthalpy of the reaction. And there's that answer. Okay. Now, the next thing we're supposed to do is we're supposed to draw an energy level diagram for all of this for the various enthalpies here. So to draw an energy level diagram, we need to write out some enthalpy of formation reactions. So we have CH4 gas, we have Cl gas, we have CH3Cl gas, and we have HCl gas. So when we write out the reaction for each of these, we start off with this as the product, and we make exactly 1 mole of it. We separate it into its elements. We do the Hankel-Briff, and then we add the states. After you add the states, you add coefficients to the reactants to make sure it's balanced. So this is the enthalpy of formation reaction. So for Cl, We put Cl here. We start off with Cl, and then because it's a Hanckelbrief, we put a 2. It stayed as a gas, and then to balance it, we have to put a 1/2 here. And this reaction, we put CH3Cl gas. There are 3 elements: carbon, which is a solid, hydrogen, which is a Hanckelbrief, and chlorine, which is a Hanckelbrief. And then to balance it, I have to put a 3/2 in front of hydrogen, so I get 3 hydrogens, and a 1/2 in front of chlorine, so I get 1 chlorine. And for the last one, we have H2 gas plus Cl2 gas, and we need a 1/2 in front of each of these. And the reaction that we're trying to get is CH4 plus 2Cl gives you CH3Cl plus HCl. So that's what we're trying to get. So in order to get this, I'm going to look at each of these reactions and try and achieve this through these reactions. And here's how we do it. I want CH4 in my answer. And there's only one reaction here that has CH4 in it, and it's the first one. In this reaction, CH4 is a reactant or a product. Here, it's a reactant. So I need to change this equation so it shows me CH4 as a reactant. Now, the value for this is minus 74.87 kilojoules. The value for this one is 121.3 kilojoules. The value for this one is minus 82.68 kilojoules. And the value for this one is minus 92.31 kilojoules. So I'm going to take this first reaction and reverse it. And I have to reverse that value, positive 74.87 kilojoules. Now, to get my 2 Cls, I need this reaction, but I need the Cls as a reactant, and I need 2 of them. So I'm going to reverse this reaction and double it. So when I double Cl, I get 2 Cl gas. When I double 1/2 Cl2, I get 1 Cl2. And then I'm going to have 2 times negative 121.3 kilojoules. So here, since I reversed the reaction, I take the negative of that. And since I doubled the reaction, I also double it. Now, in this next reaction, you can see this is the one that introduces the CH3Cl, the methylene chloride. And this is a product, and that's the product. So I'm going to use this reaction as is. And this number as is. Now, this last reaction is how we get HCl, and we need 1 HCl, so I'm going to use this reaction as is. And minus 92.31 kilojoules. So when I add these all up together, I should get that answer I got before, the 342. So this is another way to do that problem that we looked at before. It takes much longer. But nonetheless, let's go through the process here and add everything together. Now this doesn't cancel with anything, and that's good. This does not cancel with anything, and that's good. This does not cancel with anything, and this does not cancel with anything. So hopefully everything else cancels. So let's take a quick look at that. This carbon cancels with that carbon. 3/2 hydrogen plus 1/2 hydrogen are 2 hydrogens total. 4/2, 2. So these cancel with these. 1/2 chlorine plus 1/2 chlorine makes 1 chlorine. which cancels with 1 chlorine. So indeed, we get the reaction that we want. Okay, Jackie, I'm going to put you on the spot here in just a moment. Now, when we add these numbers up together, you're not on the spot yet, Jackie. We've got 74.87 minus 121.3 times 2 minus 82.68 and minus 92.31. And I get negative 342.72 kilojoules, which is the answer we got before, except for one little glaring omission that you guys should have noticed, but you didn't say anything. This is a negative and this is a negative. What should this value be? Turn your mics on.
A negative.
Negative. And so this is exothermic, right? Because that value is negative. Okay, so you see we get the same value either way.
I also
Now
think
this is really what we're doing when we do this right here. This is what we're really doing. So this is a shortcut. So why did I do this? Because we're supposed to show the energy level diagrams between all of these. Okay, so I'm going to say this is minus 242.6 kilojoules right there. Okay, now let's go ahead and try and write all of these down. This, all 5 of them. So where do we start? And the answer is when you have 5 of these, start with the low one, and that's this one. So Jackie, now you're on the block here. Turn your mic on. Since that's a negative, do I draw an arrow up or an arrow down?
you would draw an arrow down.
That's right. Good. And then we put little lines at the ends of the arrow. And always on top of the line, you write products and reactants. And just like the arrow here, the products go at the head of the arrow. And the reactants go at the tail, but always on top of the line. Okay, so there we go. All right, so next I want to incorporate any one of these into these. And it's my choice of how I want to do it. Now, let's say I wanted to incorporate this one here, the CH4 gives you carbon plus 2H2. Would this be an arrow going up or an arrow going down?
An arrow going down?
Positive.
Oh, an arrow going up then.
It's an arrow going up. And the arrow wants to end where? At carbon and hydrogen and begin here. So I could actually do this. So here's my CH4. What do I end up with here? Carbon plus 2 hydrogens. Now here you'll notice one CH4 makes these things, but I also have these 2 chlorines. What happens to them in this reaction? And the answer is not a darn thing. So I'm going to add them back in. And here, this basically says we're going from this plus 2 of these to this plus 2 of these. So this is the real reaction between these 3 things. Okay. So now let's continue. So we checked off the things that we put in. And here, since I've got these two chlorines and I've got these two chlorines here, I'm going to incorporate this guy next. So based on this, I want to start at my two chlorines, which are right here. Based on this number being negative 242, do I want to draw an arrow going up or an arrow going down?
Down.
How far?
242.
242. And notice this arrow is longer than this arrow because this arrow is 74 long. This one's minus 242, so it's got to be longer than that. You'll also notice I'm not trying to make this proportional at all. I'm just trying to show relative lengths, like this is longer than that. Okay, so here we go from our two chlorines to Cl2. So we make Cl2 gas. So in this reaction, where two chlorines make one Cl2 gas, what happens to the carbon and the hydrogen? And the answer is not a darn thing. So I just bring them down. Okay, so far we have three reactions incorporated here. 1, 2, 3. Now we have to incorporate two more. Let's take a look at this one here. This one that ends up at CH3Cl, and there it is. So I want to draw an arrow going down 82.68. And starting from carbon solid plus 3/2 H2 plus 1/2 Cl2 to get my CH3Cl. Now in this reaction, what happens to the HCl? Not a darn thing. And then now I just have my last reaction put in here, this one between 1/2 H2 and 1/2 Cl2 to give me HCl. And it's actually right here. And this shows the relationship between all 5 reactions. And I'm willing to bet that if we just look at these 3 values and add them up without regard to the negative, so I'm going to add them up, 242.6 plus 92.31 plus 82.68. This whole distance here is 417.59 kilojoules. What do you think will happen when I add these two numbers together? 342.72 and 74.87. When I add them up together, I get 417.59 kilojoules because these are the same distance, as it were. When we take a look at each one of these lines, let's take a look at what we have here. Carbons, we've got 1. Hydrogens, we've got 4. Chlorines, we've got 2. What do we have here for carbons? 1. How many hydrogens? 4. How many chlorines? 2. Look at this line. How many carbons? 1. How many hydrogens? I'm missing 1. So I need to fix that. I should have 4 hydrogens. I've only got 2. And that's because when I wrote this down here, I forgot the 2. So I've got 4 hydrogens and I've got 2 chlorines. Every line is balanced. We have not lost any elements or atoms or anything like that. So if you want to take a look at what are the things that you do first, what's the first thing you do? Start with the longest line, the biggest change in energy. If the change in energy is positive, arrow up. If it's negative, arrow down. What do you put at the head of the arrow? Always products. What do you put at the tail of the arrow? Always reactants. And once you get your first one in, look for another reaction that has either the reactants or the products in it and make the connection, following the rules of arrow up for positive and arrow down for negative. This one was probably a little tough for you guys, drawing an arrow up from what I've already drawn in, because we haven't seen that before. All right, so that's a tough one. Do you see why I wrote all these reactions out? How in the world would I be able to do this if I didn't have the reactions? And the answer is, how in the world? No way. Impossible. All right, so that's an energy level diagram. You want to try another one?
Yeah, sure.
Let's see. I think 87 might be a little easier. I'm not sure. I may have done 87. So 87, they give you all the reactions right out of the gate. So they give you strontium solid plus carbon solid plus 3/2 O2 gas gives you SrCO3 solid. And they give you Sr solid plus 1/2 O2 gas gives you SrO solid. And they say that the change in energy for this reaction is minus 592 kilojoules. They give us SrO, whoops. Let me wipe that out because I want to use that space. SrO solid plus CO gas gives me SrCO3 solid. And the change in enthalpy for this reaction is minus 234 kilojoules. And they give us this one here, graphite, which is a solid, plus O2 gas gives you CO2 gas. And the enthalpy of this reaction is minus 394 kilojoules. Now, of these four reactions, this one is a formation reaction, and this one is a formation reaction. And the reason they're formation reactions is because you're making exactly 1 mole of something from its elements. 1 mole of something from its elements. This is not a formation reaction because you're making this from compounds, not from elements. So these are compounds. This is not a formation reaction because you're making this. Oh, this is a formation reaction. And this is probably what we need to find out, the answer to that. Okay, so let's draw an energy level diagram to find out what the answer is. So which of these 3 equations do you want to start with? Who wants to raise their hand and say, me, I'll tell you. Which of these 3 do you want to start with? You got a 1 in 3 chance of getting it right.
For the first equation, you could just leave it as it is.
When you say first one, which one are you talking about?
Oh, the solid strontium plus the 1/2 mole of oxygen.
Okay, so the first reaction with energy. So you want to start with that one. Why?
Because you would want to get solid strontium in like the final formation reaction.
Wrong answer. It's the right answer, but for the wrong reason.
Is that for the biggest change of energy?
Biggest number.
Yeah.
That's why. So how long should I draw my line? 592 long. So we're going to say that that's 592 right there. What do I put at the top? SR solid plus 1/2 O2 gas and SRO solid at the bottom. So I've got this in my energy level diagram. Okay, and usually once I get my start, I just try and find another equation that has this stuff in it. So is there another equation that has SRO solid, and it's right here? So I want to put this equation in. And here's the number I have to work with. So do I go up or down based on this? And the answer is I go down. How far? Minus 234 kilojoules. And what do I put at the bottom? The products, SrCO3 solid. And up here, I have to put in CO gas. So this is all balanced. One strontium, one strontium, one carbon, 1, 2. What am I missing here? Oh, I wrote the equation down incorrectly. This is supposed to be a 2. So that's a 2. So 1, 2, 3 oxygens, 3 oxygens. Are these balanced with this above? And the answer is no. We got to put a CO2 in here, and I think then it would be balanced. One strontium, one strontium. One carbon, one carbon. One oxygen plus 2 oxygens for 3 oxygens and 3 oxygens. So I've got that equation in. Now let's put this equation in. And this one's a tough one because we have CO2 here and we have CO2 here. So where do we want to put this? And since I don't know, I'm going to back off of this guy and go to this one. This one is pretty obvious because I need my strontium carbonate as a product, and I have it right there. So here, I'm going to have some sort of reaction that's going to go in the opposite direction, hopefully, and not any further down. So with that in mind, I'm now thinking I want to go back to this guy. And here, when we have this CO2 as a product, what am I thinking I want to do? I'm thinking I want to use this guy right here. And the reason for that is simply because I have oxygen and CO2, and I need, actually, yeah. This one's going to take some thinking. Let me think about this. Because we have 2 options. One option is this. I'm going to write both options down, one in pencil. Minus 394. And I get my CO2. And I have my carbon and my oxygen. Okay. And the other option is I do this, minus 394. There's my CO2, and I have my carbon solid plus my oxygen. So those are the 2 options. I'm going to erase the second one. And we're going to see where this guy fits into place. It looks like it's right here. This plus that. This doesn't have carbon and oxygen. So now I know what I want to do. now I can see that what I would like to do is probably try and put this one in next, but not put a length associated with it. One of the things that we know is that most enthalpy of formation reactions are negative. So if I start off with strontium plus 3/2 oxygen plus carbon, it's going to go down. And now that I think about it, this is what I'm going to do. Change in enthalpy is equal to question mark. And here I have my strontium carbonate. So here I'm going to put strontium solid plus carbon solid plus 3/2 O2 gas. So that's what we want to figure out. And here I have 1 strontium, 1 carbon, and 3 oxygens. So I'm still balanced, right? So now I'm wondering, where does the other equation fit in? There's something I'm missing here. What am I missing here, folks? Let's make sure I've written the equations down correctly. Huh. This one's a tougher one than I thought. See, this one is here. And then this one was here. And this one is here. That makes sense. So how do we fit this one in? Let me think about that.
Is it possible there's an error because we haven't found like the energy of formation for the first equation?
For this one?
Yeah. Like
No.
it could be possible. Oh, okay.
No, because we should be able, well, let's see if we can add these 4 up to get this reaction. Add these 3 up to get the reaction. I think actually, so here, let's take these 4 equations, see if we can get this above reaction. So we've got strontium solid plus 1/2 O2 gas gives you strontium oxide solid. And that's minus 592 kilojoules. And the reason we like that one is because that's SR. This one will give us the carbon. So we'll add carbon graphite plus O2 gas gives you CO2 gas. And this is minus 394 kilojoules. And then we need our strontium carbonate, and that's where we have this reaction. Okay, so we put all 3 of these reactions together, and let's see if they add up to what we want. Okay, so these cancel. We're left with strontium solid plus carbon solid plus 1/2 and 2/2, 3/2 O2 gas, and CO2s cancel. And then they give you strontium carbonate. And when we add these numbers up together, oh, I see. I see. My mistake. But do you see how all these add up to what? Minus over 1,000? So what I was not able to do was make the jump that maybe this here should actually start way up here. And that's exactly what's happening. So here, when you add these three values up, 592 plus 394 plus 234, we get minus 1,220 kilojoules. So what did we learn out of all of this? I think what we learned is do Hess's law first and add them all up, and then try and write the energy level diagram. So here are the four reactions. Which one are we going to write first? So there's the first reaction. Now, which one do you want to incorporate next? I'd go ahead and put this one in. We have strontium plus 1/2 oxygen. Gives you the strontium oxide. Now, when we use 1/2 oxygen, how much oxygen do we not use? 1 oxygen. How much carbon do we use in this reaction? No carbon. So those come on down. And this seems like a good time to use the C plus the O2. C plus O2 make you CO2. What happens to the strontium oxide? Nothing. And then you have your minus 234 kilojoules right there when those two react and make strontium carbonate. So if you're going to draw an energy level diagram, what's your first step going to be?
Determine the biggest energy. And
Nope.
Draw.
There's something we do even before that. You see, this was the biggest energy, right?
Yeah.
But we didn't know that beforehand.
We have to find it.
So it's called Hess's law.
That's Hess's law. Yeah.
So when you say find it, do Hess's law. So add up all of these and get the last. And then what? The biggest. And then after that, whichever order makes the most sense. Are you with me? Okay, so now I'm going to give one for you guys to do. Are you ready? Give me a thumbs up if you're ready. Okay, so I'm going to write 3 reactions. Remember, you don't get to look at your notes. Whoops, solid. And I want you to find out this reaction here. And then I want you to draw an energy level diagram without looking at your notes. See if you can do it. Give me a thumbs up when you think you're done. And then we'll do one more. I rewrote this equation a little below so that's a little more neat. All right. Did you get that? Did you do okay, Harry? Okay, I'm going to give you another one. This is not in your book. Okay, give me a thumbs up when you're done. If you get stuck and you don't want me to know it, give me a thumbs up. If you figure it out and you know it, give me a thumbs up. So the deal is when I get 3 thumbs up, I know to go ahead and show you how to do it. Because you either think you got it or you got stuck. And I won't know. Okay, so I'm going to explain it to you. If this is our goal, we want to have a reaction below that has H2O liquid as a product. And there it is. And here, if we want to get this reaction above, we want H2O gas as a reactant. This is pretty close. We have H2O gas, it's a product, but we can make it into a reactant. So here I'm making it into a reactant by writing the equation backwards. And when I say backwards, I mean I'm taking the product and making it a reactant, and I'm taking the reactants and making them products. But in writing the equation backwards, I also have to take the negative of this amount. So that's going to be positive 241.8 kilojoules. And when we add these together, we can basically cancel things on the left and the right that are identical. H2 gas and H2 gas cancels. 1/2 O2 gas and 1/2 O2 gas cancels. So we can add these two numbers together and we get negative 44.0 kilojoules. So for these reactions, which one do we write first? The top one, because it's got the biggest number. So put the product in at the head of the arrow, put the other stuff at the beginning or the tail of the arrow. And we've got our first one written in. Now I'm going to incorporate this guy. And for this guy, you can see that I want to end up at H2 and half O2, and it's a positive, so I'm going to draw an arrow going up. Now, why is this arrow shorter than that one? And the answer is because it's only positive 241.8 kilojoules. It's not positive 285. So where is this one? Well, you know it's a negative, right? So I got to draw an arrow going down, and there it is. Any questions on that one? Okay, let's do one last tough one. So here are the reactions. Okay, so those are the three reactions, and you're supposed to find actually you're going to find this. Oh, wait, I'm sorry. That's fine. So find that. And then draw an energy level diagram. So for this one, it's going to take you a little while. I'm going to pause the recording and you're going to give me a thumbs up when you have it done and you're ready to hear the answer, or you're going to give me a thumbs up about this particular problem, Harry.
No.
Oh, a different problem.
Yeah.
So let's take a look at this. Can everyone see that we have 2 borons here? And we have 4 here. So I'm going to take this first equation and half it. So there's the first equation halved. Here we need 3 H2s. So I'm going to take that equation and triple it. And here we need 1 B2H6. So I'm going to take this equation and reverse it. Now, this is hopefully what we're going to keep out of all of this, and hopefully everything else goes away. So let's find out. So the B2O3 go away. The H2O doesn't go away, does it? Oh, I made a mistake, people. My apologies. This one here is supposed to be plus 3 H2O. So that'll fix everything. So the H2Os do go away. The O2s go away. And we do get what we want. And so now I need a new pen. That one's running dry. Let me see what I get here. 2543.8 times 0.5. Take the negative of that. Then plus 3 times negative 241.8. Then plus 2032.9. And I get 35.6 kilojoules. So this should be around 250. This should be around 750. So that seems about right. Is that what you got for the answer? Give me a thumbs up if that's what you got for your answer. 35.6 kilojoules. Okay. Now remember, You might have screwed up because I did not write this equation down correctly. Okay, so now which of these am I going to write first? This one, which is about minus 1250, this one, which is about minus 750, or this one, which is about 2000. I'm going to write this one first. So I'm going to draw an arrow up that's 2000 long, 2032.9 kilojoules. And at the bottom of the arrow, I'm going to put these things here, 3H2O and B2O3 solid. And at the top of the arrow, I'm going to put B2H6 plus 3O2 gas. Okay, so I've got that one in. And since I've got the B2H6 and the B2H6, I'm going to put this one in next. This one is positive 35. So this one's going to go up 35 to 2 Bs plus 3 H2s. Now I'm also going to put plus 3O2 gas because these don't react, but they're still going to go up to there so I can have a balanced lines everywhere. So I got that one in. And here I've got H2 and O2. So I've got my 3 H2s and half of these react. And this is going to be minus 3 times that. So this is minus 725.4 kilojoules. And at the bottom of this, I'm going to put H2O gas. But here, since I'm starting here, the borons don't react. Plus, I only use half of the oxygen. And then finally, I'm going to put this reaction in where I have 2 borons, 3/2 oxygen, and I make this B2O6. And I got my 3 H2Os. And here, I forgot to write down that my product are actually 3 H2Os, and so it all works out. So in hindsight, I probably could have written this a little bit better, but it looks good enough to me. All right, any questions on this one? All righty then. Harry, go ahead.
It's just a clarifying thing with the specific heat lab.
Sure.
So with doing the boiling the water part, what am I doing that in?
A pot.
Oh, okay. I guess that just makes sense.
What I would do is when I boil something like what might I use this for? Sometimes I deep fry things, Harry.
Right.
And so I've got this bamboo utensil that ends with a basket made out of metal. Okay. And you use this to pull stuff out of your deep fryer so that the oil doesn't come out with the stuff that you deep fried. So you kind of know what I'm talking about, Harry?
Yeah, I could picture it.
Yeah, it looks like this wooden handle, and it comes down to a thing that's like a metal basket.
Right.
I was thinking if it were me, I'd probably put this guy in my pot with the dimes inside of it. Because you could leave the whole thing there in your pot for about 5 minutes and the dimes would heat up, right?
Right.
And when you pull the dimes out of the pot, you don't have water sticking to the dimes, right?
Right.
And then you could take the dimes and just pour them into your water. And you've added hot dimes to your water.
Oh. All right.
Otherwise, if you do it this way and you don't use this guy, you're going to have to pour all the hot water out and then pour the dimes into your cup.
All right.
And that seems like a good waste of hot water because you could use that hot water for the pennies next.
Yeah,
Does that make any sense?
that makes sense.
Yeah. So that's the
then-
way I'd probably do it. Just because it'd be easier.
And then-
Scientists are always trying to look for tricky ways to do things that aren't really tricky. They're just more like common household sense. And that's what I would do.
Okay,
Now, you know what the answer is supposed to be close to because you know pennies are made out of zinc and you know that dimes are made out of copper. So your specific heat capacity for the dime should come out close to that for copper. And you can look that up. And
Right.
for your pennies, it should come out close to zinc. And you can look up the specific heat capacity for zinc and see if you get something close to those values. If you're not getting close to those values within, say, 10 or 20%, there's something wrong with your technique. Okay?
okay,
Or your calculations.
all right.
Fair enough?
Yep.
Okay. Any other questions, folks?
One more. With the assignment, was this supposed to be more on it?
No, the assignment is basically do all the stuff in your lab notebook. And I'm going to be grading your lab notebook to see if you have all these things done, but I'm not going to be looking to see pretty much how well it's done. The lab assignment, I'm going to be looking at your calculations and discussion pretty closely.
Okay,
So it's the amount of detail I'm going to be looking at for the different assignments. So this is a way to get you to understand that essentially the lab is what you're supposed to be learning. And that's going to become the assignment, so to speak.
okay, all right. Well, thank you.
So it's actually going to be a little less work for you sometimes. Okay?
All right,
All righty then. Turn your mics off, say goodbye. We'll see you Friday, hopefully, for the next section.
all right.
Bye,
Thank you, everyone.
guys.
All right. Bye, everyone.